friends, welcome to my lecture on partial ordered sets. This third lecture on partial ordered sets, that is posets. Let us first define what do we mean by a maximal element in a poset. An element A in a set S, which is a poset, is said to be maximal if no other element succeeds A. That is, if A precedes X, then it must imply that A is equal to X. A maximal element in a poset need not be unique. So, this is a very important point. A maximal element in a poset need not be unique. There could be more than one maximal element, and there may not be any maximal element. All those elements which appear at the highest levels of a Hesse diagram of a poset are maximal elements. So, from the Hesse diagram we can easily see what are the maximal elements. Now, let us see, for example, we have this set x equal to 2, 3, 6, 12, 24, 36 and let it be a poset with divisibility relation. Then we have to show that 24 and 36 are maximal elements. So, we will draw its Hesse diagram, and then we from the Hesse diagram we shall be able to see the maximal elements. So, let us draw the Hesse diagram. So, this is 2, then we have now since it is a divisibility relation, 2 does not divide 3 or 3 does not divide 2, okay. 2 divides 6, okay. So, we have 2 divides 6, okay. Then 6 divides 12, okay. 6 divides 12. So, we have 12 here, 12 divides 24, okay. So, we have 24 here, and then then we have 3, then we have 3, okay. 3 divides 6. So, we have 3 divides 6, okay. 6 divides 12, and then 12 divides 24, 12 divides 36, okay. 12 divides 36, okay. So, we can see this Hesse diagram, 2 divides 6, okay. 6 divides 12, 12 divides 24, okay. 3 divides 6, okay. 6 divides 12, 12 divides 36, okay. Now, we can see here 24 and 36, they are the maximal elements. Why they are the maximal elements? Let us go to the definition again of the maximal elements. An element is called maximal if no other element succeeds A, that is, A precedes X implies A is equal to X. So, you can see that there is no element that precedes 24 and 36 here. So, 24 and 36 are maximal elements of the poset X. A poset may not have a maximal element. For example, let us consider the set of integers Z, okay. Let us consider the set of integers with the usual less than or equal to relation, okay. Then no element is a maximal element, okay. You take any element, we can always find an element which is greater than that. So, there is no element which is a maximal element. Now, let us go to minimal elements. Analogously, an element B in a poset S is called a minimal element if no other element precedes B. That is, if bi precedes B, then bi must be equal to B. A minimal element again need not be unique. There could be more than one minimal element, and there may not be any minimal element. All those elements which appear at the lowest levels, okay, at the lowest levels of a Hesse diagram of a particular partially ordered set are minimal elements. So, it is easier to locate the minimal elements of a poset if we draw the Hesse diagram. The elements that occur at the lowest levels will be the minimal elements. Now, a poset may have more than one minimal element. Let us say, for example, let us consider this poset 2, 3, 6, 12, 24, 36, okay, with divisibility relation. Then 2, again we can see 2 divides 6, okay, 6 divides 12, 12 divides 24, okay, and then 3 divides 6, 3 divides 6, 6 divides 12 and 12 divides 36, Okay. So, here you can see 2 and 3 occur at the lowest levels of this Hesse diagram, therefore, 2 and 3 are minimal elements here. A poset may not have a minimal element, you see here a poset may not have a minimal element. For example, if you consider the set of integers again, okay, set of integers z, okay, with the usual relation less than or equal to, then we know that it is a poset, because you take any two integers, okay, any integer, then a belongs to z, this less than or equal to is a reflexive property, because a is less than or equal to a, and if you take a b belong to z, then a less than or equal to b, b less than or equal to a, and b less than or equal to a implies a equal to b. Okay. If you take a b c belonging to z, okay, then a less than or equal to b and b less than or equal to c implies that a is less than or equal to c. So, the set of integers with this relation less than or equal to is a poset, okay, and clearly it has no minimal element, because you take any element, we can always have an element which is which precedes that element. Okay. So, this has no minimal element. So, the set of integers with the usual relation does not have a minimal or a maximal element. Now, every non-empty finite poset has at least one minimal element and one maximal element. So, let us show that every non-empty finite set has at least one maximal element, and then a similar proof we can give for minimal elements. So, let us say let S be a finite non-empty poset. Okay, with the order relation, partial order relation, this precedes. Okay. So, since S is a non-empty set, it must have an element say x naught. So, if x naught is the maximal element, if x naught is the maximal element, then we are done. Okay. If x naught is not the maximal element, then there exists x 1 belonging to S such that x naught precedes x 1 and x naught is not equal to x 1. Okay. If x naught is not, if x naught is not the maximal element, then there will always exist an element x 1 belonging to S such that x naught precedes x 1 and x naught is not equal to x 1. If x 1 is the maximal element, then again we are done. If x 1 is not the maximal element, then there will exist x 2 belonging to S such that x 2 x 1 precedes x 2, okay, x 1 precedes x 2 and x 2 is not equal to x naught. Okay. So, we can go on iterating this process. If x 2 is not a maximal element, then we will get an element x 3 such that x 2 precedes x 3 and x 2 is not equal to x 3. So, in this manner we get a sequence, okay, iterating this process. We obtain a sequence x naught precedes x 1, x naught, x 1, x 2, x 3 and so on. We get a sequence in S, okay, which satisfies this order relation, x naught precedes x 1, x 1 precedes x 2, x 2 precedes x 3 and so on. Okay. Since S is a finite set, okay, when you get this sequence x naught, x1, x2, this infinite sequence, then there are two possibilities. At some stage we get the maximal element, okay, we get the maximal element, we get a maximal element in S, say some xi, okay, we stop. If we do not have a maximal element, then because of the fact that S is a finite set, what will happen that for I, for some I less than j, xi will be equal to xj, xi will be equal to xj. Now xi precedes xi plus 1, xi plus 1 precedes xi plus 2 and so on xj minus 1. Okay. So, xi precedes xj minus 1, okay, and what we have here xi equal to xj. Okay. Xj minus 1 precedes xj minus 1 precedes xj. Okay. Further xj minus 1 precedes xj and xj is equal to xi. Okay. Xj is equal to xi. Okay. Xj is equal to xi. So, by transitivity this see xi precedes xi plus 1, xi plus 1 precedes xi plus 2 and so on xj minus 1. So, by transitivity xi precedes xj minus 1. Okay. Now, xi precedes xj minus 1 and xi precedes xj minus 1. Further xj minus 1 precedes xj and xj is equal to xi. So, we have xj minus 1 precedes xi. Thus xi precedes xj minus 1 and xj minus 1 precedes xi. Okay. So, by antisymmetry xi equal to xj minus 1, but xj minus 1 is precedes xj. Okay. xj minus 1 precedes xj. Okay. Xj minus 1 strictly precedes xj. Xj minus 1 is not equal to xj. Okay. Xj minus 1 is not equal to xj and xj minus 1 precedes xj, and so xj minus 1 precedes xj and xj is equal to so xi is equal to xj minus 1, xj minus 1 precedes xj. Okay. Xj minus 1 strictly precedes xj. So, this means xi strictly precedes xi. Okay. So, thus xi strictly precedes xi. Okay, which is impossible, because xi strictly precedes xi means xi is not equal to xi and xi precedes xi. So, so here what we do, xi precedes xj minus 1, xj minus 1 precedes xi. Okay. Therefore, by antisymmetry xi is equal to xj minus 1, but xj minus 1 strictly precedes xj and xj is equal to xi. So, xi strictly precedes xi. So, that is impossible. So, the finite set S must have a maximal element, and similarly we can show for minimal element the existence of a minimal element. Now, let us go to the this example. Let S be equal to 2, 4, 6, 12, 20 and S be a poset by the order relation divisibility. Then let us find the maximal and minimal elements of S. So, let us draw the Hesse diagram. 2, 4, okay. Then we have 6, 2, 4, then we 4 divides 12. So, we have 12 here, okay, and then we 12 does not divide 20. Okay. Now, what we have, 2 divides 6. Okay. So, we have 6 here, 2 divides 6, 6 divides 12. okay, 6 divides 12 and 4 divides 20. Okay, 4 divides 20. So, now in this Hessy diagram what do we notice? There are two maximal elements. Maximal elements are 12 and 20. They are at the highest levels of the Hessy diagram. Maximal elements are 12, 20 and minimal element. Minimal element is the one which occurs at the lowest level of the Hessy diagram. So, minimal element is 2. Okay. Now, let us go to this example. Let T be equal to 2, 3, 4, 16. Let it be ordered with the divisibility. Then again let us find the maximum minimal elements of T. Then let us draw the Hessy diagram for this. So, 2 divides 4, okay, 4 divides 16, okay, and we have 3. Okay, 3 and 2 are not comparable because 2 does not precede 3, 3 does not precede 2. Okay. So, and 3 does not precede 4, 3 and 4 are also non comparable, 3 and 16 are also non comparable. So, here the maximal elements are 3 and 16, okay. Minimal elements are 2 and 3. Now, suppose f is equal to a b c d e, okay. F equal to a b c d e be ordered as in this figure, okay. Find all the subsets of f in which the element c is a minimal element. So, the subsets of f in which the element c will be the minimal element means we should consider all those sets, okay, subsets of f which contain c, but do not contain a. Okay. So, the minimal subsets of f are the subsets of f in which c is the minimal element. They are singleton set C, okay, singleton set C, then we can write CE, okay. We should see that the set contains C, but it does not contain A because A occurs at the lowest level of the Hessy diagram. So, CE we can write CD, CB, then we have DCE, then BDC, and then BDCE. Okay. So, all those subsets contain C, but do not contain A. Now, singleton set C we have taken, CE we have taken, CD, CD we have taken, BC we have taken, and then we have DCE, DCE, then we have BDC, and then we have BDCE. We also have BCE. Okay. So, there are 8 sets, there are 8 sets subsets of f in which C is a minimal element. Okay. Now, let us go to the case least elements. Let P be a poset with this order relation precedes if there exists an element A in P such that A precedes x for all x belonging to P, then A is called a least element in P. The least element is also called first element or 0 element of P. Now, if the least element exists, then we can easily prove that it is the unique element. It may happen that the least element does not exist. Okay. So, if the least element exists, it will always be unique. So, let us prove this fact. So, let us say let there be two elements A and B in P which are least elements of P. We shall show that they have to be equal. Then by definition A strictly A precedes x, okay, for all x belonging to P, and B precedes say x for all x belonging to P. Okay. Now, since A precedes x for all x belonging to P and B is an element of P. So, A precedes x for all x belonging to P implies that A precedes B. Okay. Further, B precedes x for all x belonging to P implies that B precedes A, because A is also an element of P. Now, A precedes B and B precedes A. Okay. Let us use anti-symmetry. So, then if A precedes B and B precedes A, we have A equal to B, okay, by anti-symmetry. So, if at all the least element exists, it will be unique. Now, greatest element, let P be a poset if there exists an element A belonging to P such that x precedes A for all x belonging to P, then A is called the greatest element in P. The greatest element is also called the last element or unit element of P. If it exists, it is unique. Like it can be easily shown that the greatest element has to be unique. If it exists, we can give this argument similar to the case of the argument given in the case of least element. So, it may happen that the greatest element does not exist. Now, let us look at some examples. Suppose S is equal to A B C. Okay. We consider the power set of S with the inclusion relation. Okay. Power set of S with the inclusion relation is a partially ordered set, that is, it is a poset, we know this. Okay. Now, consider this subset of P S phi B C A C. The set A consisting of phi singleton set B singleton set C and then the set A C, okay, is clearly a subset of P S. Then phi, okay, phi is contained in every set, phi is contained in every set belonging to the set A. Phi is contained in phi is contained in B, phi is contained in C, phi is contained in AC. Okay. So, phi is contained in every set in the set A. So, phi is the least element by the definition of the least element, and it has no greatest element. Why? Because there is no element in A which includes every other element of A. Okay. That means all the elements of A are subset of that element. No such element is there. If you take this AC, then this AC element contains C, it contains phi, but it does not contain B. Okay. So, this A has no greatest element. Now, if you take the set B to be this phi A B A B, okay, then again phi is the least element of B, okay, and A B, you can see A B is the greatest element, because A B every set here, every element of B is a subset of A B. Okay. Phi is a subset of A B, singleton set A is a subset of A B, singleton set B is a subset of A B, singleton set the set A B is itself a subset of A B. So, this A B is the greatest element. Now, let us define supremum and infimum. Let A be any subset of a poset S. An element M in S is called an upper bound of A if M succeeds every element of A. Okay? That is, M is an upper bound of A if for every x belonging to A we have x precedes M. If an upper bound of A precedes every other upper bound of A, then it is called the least upper bound or supremum of A and be denoted by sup A. An element small m in S is called a lower bound of A if M precedes every element of A, that is, M is a lower bound of A if for every x belonging to A we have M precedes x. If a lower bound of A succeeds every other lower bound of A, okay, then we call it as the greatest lower bound or infimum of A and be denoted by inf A. Now, let us look at this figure, okay, this Hesse diagram. So, let B equal to A, B, C, D, E, F, G, okay, let it be ordered as shown in this figure, okay, x is equal to C, D, E. We have to find upper and lower bounds of x. Okay. So, upper bound, let us again go to the definition of upper bound. Upper bound, an element M in S, okay. An element M in S will be called an upper bound of A if M succeeds every element of A. So, let us see which element of B succeeds every other element of X. Okay. So, we have here C, you can see C, D, E, okay. This is C, D, E, okay. So, now you can see F, E and G, okay. F, E and G are the elements in B which succeed every other element of X, okay. E succeeds C, E succeeds E, E succeeds C, E succeeds D, okay. And F succeeds E, F succeeds C, F succeeds D. Similarly, G succeeds E and G succeeds C and G succeeds D. Okay. So, upper bounds here are E, F, G. Now, let us look at lower bounds. So, lower bounds are those elements of B, okay, which precede every other element of X. Okay. So, let us see, we have C, D, E here, this is C, okay, this is D, this is E. Okay. Now, which elements of B precede C, D, E? There could be two elements, A and B. Okay. Now, A precedes C, A precedes E, A precedes D. Okay. So, A is clearly there, A is a lower bound. Okay. Now, B is not a lower bound of this set X because B does not precede C. Okay. B and C are not comparable. Okay. So, since B does not precede C, okay, we have a lower bound as only A. Let us take another problem. Let W be equal to A, B, C, D, E, F. Let it be ordered as shown in this figure and by be equal to B, C, D. We have to find the upper and lower bounds of by. Okay. So, now upper bound of by means every an element of W which succeeds every element of by B, C, D. Okay. So, the elements E and F. The elements E and F succeed the elements C, D and B. Okay. So, upper bounds are E and F and lower bounds are the clearly A and B, because A and B precede every element of the set by. So, lower bounds are A and B. Now, let us define similarity mapping. Let two ordered sets are called similar if there exists a one-to-one correspondence between the elements of each set which preserves the order relation. That is, A precedes A dash A belongs A dash belongs to A precedes A dash if and only if F A precedes F A dash. So, an ordered set A is similar to an ordered set B, be denoted by this notation, this one. Okay. So, denoted by A, this is actually called isomorphic relation. A and B are then isomorphic. So, two ordered sets A and B are called isomorphic. If we can find an isomorphism, okay, this is the isomorphism, one to one onto mapping from A to B, which has the property that for any two elements A and A dash in A precedes A dash if and only if F A precedes F A dash. So, the order relation is preserved here. Such a function is called a similarity mapping from A to B. Now, let B equal to 1, 2, 6, 8, 12, this be ordered by divisibility and W equal to A, B, C, D, E. Draw the diagram for W if the following is a similarity mapping from B into W. Okay. So, let us see, this is ordered by divisibility. Okay. So, 1 divides 2, 2 divides 6, okay, 2 divides 6, 2 divides 8, okay, and 6 divides 12, 6 divides 12. Okay. So, 1 divides 2, 2 divides 6, 6 divides 12 and 2 divides 8. Okay. Now, what we have here, 1 under the mapping F, 1 goes to E. So, we have E here, okay, and then 2 goes to D. So, we have D, okay, and then 6 goes to B. So, we have B here, and then 8 goes to C. So, we have C here, and then 12 goes to A. So, we have A here. Okay. So, draw the diagram for W. Okay. So, this is the diagram for W, SC diagram for W. Okay, using the similarity mapping. Now, let X be 3, 6, 18, 27, 3, 9, X be equal to 3, 9, 18, 27, by be equal to A, B, C, D, let it they be ordered as shown in this figure. Okay, as shown in this figure, then identify all the possible similarity mappings of X onto Y. So, one similarity mapping could be F 3A 9B, then 27C, and then 18D. Okay. Other similarity mapping could be written as say G 3A 9B, and then we can say 27D and 18C. So, there are two possible similarity mappings in this case. That is the end of my lecture. Thank you very much for your attention.